Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Okay, now to finish off part 4, we're going to look at chapter 46, which is isolation and switching. Now this actually has returned from, I think, the 16th edition, when it used to be chapter 46. Throughout the 17th edition, this content was actually in section 537, or most of this content. So it looks as if chapter 46 is new within the book. It's just moved back to where it came from. So it has a bit of coverage on the requirements or the considerations we need to take when we select switching devices or isolating devices. And one of the things we need to understand is, with regards to the methods of isolation that we have, there may be circumstances where we have to make sure we switch multi-pole or single pole. There may be locations or positions where we actually need to make sure that the method of switching is isolation or functional switching. So we need to identify the different types of switching and the requirements of those. There's going to be a lot of not repetition, but a lot of similar reference to this when we get to section 537 in selection and erection, and I will have a little peek there in a minute at a table. But for now, let's just see what the actual scope's got. So it says, chapter 46 deals with non-automatic local and remote isolation and switching measures for the prevention of or removal of dangers associated with electrical installations or electrically powered equipment, and switching for the control of circuits of equipment. So that second one, switching for the control of circuits or equipment, is like a functional or a method of control. Okay, a control circuit of circuits or equipment. You could also say that could be through some auxiliary means. The first part, non-automatic local and remote isolation. So obviously not via an auxiliary or an automated control procedure. So we're talking about isolation, or we're talking about a mechanical maintenance method of switching. For the prevention or removal of dangers associated with electrical installations or electrically powered equipment. So again, is the method of isolation, or is the method required to remove the supply a requirement to do electrical work, or is it a requirement to do non-electrical work, such as mechanical maintenance? We have to identify those are two different types of maintenance, two different types of isolation. It does say that if equipment itself is manufactured to BSCN 60204, so it's manufactured to a separate standard, the isolation requirements given in that standard are sufficient, and so this doesn't really apply. This chapter doesn't apply to those. Alright, so general 461. According to the intended functions, every device provided for isolation or switching will comply with the relevant requirements of chapter 53. Okay, we've mentioned this just a bit earlier. Chapter 53 is, it's selection and erection, and it's all about selection and erection of devices for protection, isolation, switching, control, and monitoring. And in this case, we'll be looking at 537, which is isolation and switching. So yeah, all of chapter 53 has to be referred to. In TNC and TNCS systems, the PEN conductor, so TNC and TNCS systems are obviously combined neutral conductor. TNC and TNCS, the systems where the neutral and earth are combined all to the point of intake, and if they remain combined, it's still a TNC system, which we don't really allow here. Or if it's then separated, it becomes a TNCS system, known as a PME, and it has a PEN conductor, so it's a protective earth neutral. The PEN conductor shall not be isolated or switched. In TNCS and TNS systems, isolation or switching of the neutral conductor is not required if protective equipotential bonding is installed, and either the neutral conductor is reliably connected to earth by low resistance to meet the disconnection times of the protected devices in accordance with the requirements of chapter 41. So being a TN system, there'll be a method of connection between the neutral and the earth. Okay. And the disconnection times of chapter 41 have been achieved. Those were the earth fault loop impedances that we had, and the times with regard to TN systems was 0.4 seconds and 5 seconds respectively, determined on whether or not the circuit was a final circuit exceeding 32 amp for fixed equipment, a final circuit of socket outlets over 63 amp. Those were both 5 seconds. 0.4 was for final circuits up to 32, and socket outlet circuits up to 63. Distribution circuits were also 5 seconds. We can always go back to the part 4, chapter 41 video to remind ourselves of that if we need to. So those times have to be met. And the distributor declares that either the pen or the neutral conductor of the supply is reliably connected to the earth by a low resistance to meet the disconnection times of the protected device in accordance with the requirements of chapter 41. So you're relying on an effective, you're relying on ADS really. You're relying on the whole ZS's disconnection of supply has to be in operation. Okay. So isolation or switching of the neutral conductor is not required if that. And a good example of this, if you go to a 3-phase consumer unit, a commercial installation, if it's a TN system, a TNS or a TNCS, quite often you'll notice the fuse board will have a triple pole isolator for the 3 phases, but the neutral coming in will go to the neutral bar, the neutral terminal. So it's not been isolated, it's not been disconnected. If that actually was for a TT system, due to the high impedances between neutral and earth, we actually need to install a 4-pole isolation switch for TT systems. This is a common thing I see on the ICRs where, you know, the electrician hasn't actually thought that far with the design. You need to have a 4-pole multi-pole isolating device on a TT system. Here it says we don't need to isolate the neutral if it's a reliable TN system. Alright, so we then move on to 462. This brings our first method of switching, and this method of switching is called isolation. And that is simply this. It's an isolation device. So an isolator is a device that is going to remove the source of supply. So this is a device that is there to remove the source of energy, the source of supply, for electrical work to be safely carried out. So the requirements, it says every installation shall have provisions for isolation from each supply. So again, if you have multiple supplies, you must have an isolation method for each supply. A main link switch or link circuit breaker shall be provided as near as practicable to the origin of every installation as a means of switching the supply on load and as a means of isolation. Okay, must be able to switch on load. A main switch intended for operation by ordinary persons, so homeowners, must interrupt both live conductors. So a house or a home or a similar installation, the isolating device must be multi-pole, must be double pole. Every circuit will be provided with isolation means for all live conductors except as detailed in the regulation 461.2. And that again mentioned just now, we have reliable ZSs achieved for with the ADS protective measure on a TN system. Okay. 426.3. Devices for isolation will be designed and or installed so as to prevent unintentional or inadvertent closure. Examples of precautions are as follows. Located within a lockable space or a lockable enclosure. Padlocking or located adjacent to the associated equipment. So you couldn't technically use a local simple light switch as an isolating device. It has to have these 3 things. It must be in a... Technically, if you put it in a lockable enclosure, maybe you could, but it has to be a place that you can control. A method of switching that you can control. Where residual electrical energy is potentially dangerous or potentially present, suitable means shall be provided for its discharge. Residual electrical energy, the common example of this is capacitors. So obviously you may notice many times you isolate a piece of electrical equipment and it takes a while, but the little LEDs are still lit and they gradually fade away. This is an example of residual energy discharging. The capacitor stores charge. If you work with power factor correction equipment or with any other electrical equipment that has a significant quantity of stored capacitors, may even be an on-site rules procedure or something that says like along the lines of, at a point of isolation, you must then wait 10 minutes or so to consider discharging of the residual energy. What we're not supposed to do is short it to earth because that's obviously a unsafe working practice. So that's the safety requirements for the isolation. So it's talking more about it having to be single pole only if it's not an ordinary person location, multi-pole if it is. It also says about it having to be lockable or in an enclosure that's locked or literally on the equipment itself. Okay, and it also mentions residual energy. That's what we're talking about here about protection. Later on in 5.3, we'll also talk about identification and functionality and things like that. Moving on from that to functional switching, this is the next switching type. So that was isolation as a switching type. The next switching type is functional switching. Now, functional switching is the type of switching you are going to be giving to the users of the installation. So in the home, a functional switch is a light switch or a thermostat or maybe a pull cord. These are devices that are easy to operate, they are easy to identify, and they don't require any settings or any presets or any further skill or instruction to use safely. They're everyday things. Similarly in the workplace. Now you may have functional switching in the workplace such as a start-stop on a motor. That's absolutely fine as long as it is suitable for the user. It can be considered as a functional piece of equipment as well. Requirements for functional switching are: it should be provided for each part of the circuit which may be required to be controlled independently of other parts. You need not necessarily switch off all live conductors of the circuit. A single pole switching device shall not be placed in the neutral except for the connection of the control device for a lighting circuit as shown in figure 46.1. So there's a special circumstance about single pole switching neutral here where it's part of the control circuitry for a luminaire. In general, all current use equipment requiring control shall be controlled by an appropriate functional switching device. Appropriate, we'll look at types of switching device later in 5.3. A single functional switching device may control several items of current use equipment intended to operate simultaneously. Simply a light switch doing a number of lights. A number of pieces of equipment should be operated simultaneously. We'll use one switch for that. They'll ensure the changeover of supply from alternative sources shall switch off all live conductors and will not be capable of putting the sources in parallel unless the installation is specifically designed for this condition. So if your functional method of switching is like an interlock or a switch that switches in one source of supply to the other, unless a parallel scenario is allowed, there will need to be a interlock that will be one source of supply or the other. We'll also look at that in safety services later. We have mention on auxiliary circuits. Now, auxiliary circuits will be designed, arranged and protected to limit dangers resulting from a fault in the auxiliary circuit or an installation fault between the auxiliary circuit and other conductive parts liable to cause malfunction. Alright, so we have a section for auxiliary circuits later on and we'll look at the requirements for testing for that as well. But we do need to make sure that any faults in the circuit or installation faults between the auxiliary circuit and the wiring system, so control panels and all of that, will not cause any malfunction. Malfunction can be created in a number of ways. I mean, you can have damage within the control circuit that could create an induced voltage, which could then result in a functional switching device, or even an automatic device, falsely operating. Motor control. Motor control circuits will be designed so as to prevent any motor from restarting automatically after a stoppage due to a fall in or loss in the voltage, if such starting is liable to cause danger. We mentioned in the previous video about undervoltage protection. If we lose one phase in a three-phase motor, it will kill all of the phases, and if that phase was to then return, it won't just automatically restart if the restarting of this equipment is likely to cause any danger. So what it's saying is, if you do have functional switching on a motor, it will not be automatic unless it's been considered that is a safe consideration, a safe assessment. Earth faults in control circuits should not cause unintentional starting, potentially hazard motion, or prevent stopping of the motor. Where reverse current braking of a motor is provided, provision shall be made for the avoidance of reversal of the direction of rotation at the end of the braking if such reversal may cause danger. So if you start to reverse the current, if the braking action of the motor is to reverse the current to drive against the rotation, when you reach that point of stationary, it should stop, but it shouldn't start pushing it backwards. Yeah, so it's going forwards, and it applies reverse current to break that rotation. It slows down, and it gets to the point of stopping. We don't want that current to start driving it backwards. It needs to stop, otherwise mechanical damage could occur. Where safety depends on the directional rotation of a motor, provision shall be made for the prevention of reverse operation due to reverse of phases. Okay. The next method of switching is mechanical maintenance. Now this one is actually fairly diverse. Anytime you do work on a piece of equipment that is non-electrical, so changing a belt, changing a fan, changing a tank or sharp, changing a blade or whatever it is, in this case we've got a cooker isolator, so you could be working on a piece of cooking appliance, but it's considered acceptable for the method of I would say isolation, but isolation is a switching device. The method of removal of the supply, that a mechanical maintenance device just needs to be identifiable. So you have an off and an on, or you have a light that goes off and an on. Ideally, if the circumstances due to risk assessment say you should lock it off, you would lock it off. We're going to see all this covered more in 537 anyway, but right now, means of mechanical maintenance. Means of switching off shall be provided where mechanical maintenance may involve a risk of physical injury. The switching off shall cause the disconnection of all live conductors except as provided by 461.2 by a device suitable for isolation. Suitable means will be provided to prevent electrically powered equipment from inadvertently or unintentionally reactivating during mechanical maintenance unless the means of switching off is continuously under the control of any person performing such maintenance. So it says, it should be removed that they can turn it on unless you're there. So, you could just turn it off and work on it if it's under your control, so to speak. Okay. That was actually there. Right. And then we have emergency switching. Emergency switching is what it sounds like. It's, removing the source of supply in a single action as we possibly can. These will be provided for any part of an installation where it may be necessary to control supply to remove an unexpected danger. Where the risk of electric shock or other risk of electrical origin is involved, this emergency switching off shall cause the disconnection of all live conductors. Means emergency switching off shall act as directly as possible on the appropriate supply conductor, and the arrangement for switching off shall be such that one action only will interrupt the appropriate supply. So it should be a single operation, it should be a single action, should remove the supply that is creating the risk. It shouldn't be a combination. The arrangement of the emergency switching shall be such that its operation does not introduce a further danger or interfere with the complete operation necessary to remove the danger. So once you've isolated it, another danger should not be introduced, and once you've isolated it, actually then that should create a danger for the remedy process. Okay. And that's emergency switching. Now, we've just talked about the purpose of selecting switching for protection, but we've also talked about the types. We have isolation, mechanical maintenance, functional switching, and emergency switching. Now, with that in mind, before we finish this video, we just want to quickly look at section 537, which is on page 181, and there is a table, and it's table 537.4, and it's titled Guidance on the Selection of Protective Isolation and Switching Devices. And it looks a bit like that. So it's that table there. Now, it's fairly easy to understand this table. We've got we've got device types down the left. This table does go over the page, by the way. This is an example of the bad editing the regulations have done. Device types are on the left. They're British standard, and then there's a column: isolation, emergency switching, and functional switching, and simply whether or not the regulations considers them to be a suitable method to comply. So we've talked about what these types of switching are: isolation, emergency control, and switching are the examples given here. And if I was to say to myself, right, I'm going to use a semiconductor, can I use a semiconductor for isolation? So I'm going to go down the device lists till I find semiconductors, and I find them there, third from the bottom on that page, device with semiconductors, and it actually says no across the board of isolation and emergency switching. Okay, so I can only use a semiconductor as a functional switch. It's a functional means of operation. Similarly, a plug and unswitched socket outlet, right at the bottom of the page there, I can use as an isolation means, and I can use for functional switching. I can't use it as an emergency switch. And if we go back to the top a little bit, look at circuit breakers. A circuit breaker, the BSEN 60898, that can be used as an isolation device. We can lock them off as well, can't we? And it is a single pole device, unless you get a double pole one. We can use it as an emergency switch, which seems impractical, but okay. It's one operation, I guess. And it can be used as functional switching. So technically, if we were to disregard what we've already talked about in part 3 with division of installation and things like that and accessibility, technically we could install a fuse board in the home and just have all of the circuit breakers as the switches. You know, we can install light circuits and say, oh, go there, there's your switch. That technically is compliant with that switching arrangement in the regulations. Yeah. Obviously, assuming that we haven't considered division of installation. So that's just an example there. And again, just be aware of that table, be aware of that, because that something like that could come up in your exam. What types of switching are what. All right, but as I say, we're going to come back to this when we come to 537 doing isolation and switching. All right, so we're actually now rounding up part 4. So we've talked about in part 4. We've talked about protection, the decisions we must make to achieve protection for safety. We've talked about protection against electric shock, which was all protective measures must have basic protection and fault protection. Basic protection was protection against electric shock in fault-free conditions, barriers, enclosures, insulation, placing out of reach. Fault protection was earthing and bonding and protective devices, or in some cases isolating transformers or supplementary insulation. And there were 4 general protective measures. You had automatic disconnection of supply, ADS, which we've seen repeated a few times now. We had class 2 double insulation, we had electrical separation, we had SELV and PELV. The 4 general protective measures, and every general protective measure will achieve basic and full protection. We then had a couple of specialist ones. We then moved on to protection against thermal effects, where we talked about obviously we talked about arc fault detection devices. We talked about arcs, sparks, and particles. We talked about flammable liquids in large quantities, 25 litres or more. We also talked about the external influence risks for combustible buildings and things like that. We then moved on to protection against overcurrents, where we said about the whole issue with the whole fault loop impedances and all these other things is we established a low impedance to achieve a high fault current. Towards the end of the protection against overcurrent, we looked at calculations, the T equals K squared S squared over I squared, which told us the amount of current that would be occurring in the fault condition and whether or not the live conductors would be able to carry that current or would tolerate the temperature change for their insulation during the period of that fault. We then talked about protection against voltage disturbances. We had voltage disturbances of atmospheric origin, such as lightning and man-made events, and there was quite a large section talking about lightning and the risk assessment method. Again, It's reference material, really. It's not something that you're practically going to use, because a lot of it was directed at if you're working in substations and things like that. That closed the 4 common parts of Part 4, but then we had this last little bit where we just talked about, switching types and the protective things, the protective issues we've got to consider now. But that closes the decisions that we have to take and put into our design with regards to protection for safety. Electric shock, thermal effect, overcurrent, voltage disturbance. Having made those protective decisions, we're now going to move on to select and erect. And that means moving on to Part 5. So, see you there.